thank you all for being here, and glad to help you all imagine a world where business leaders, ahead of most governments, have abandoned oil and coal and nuclear energy in favor of alternatives that work better and cost less, efficient use, and renewable energy. Because this could solve many of the world's biggest problems without making new ones. And that world that I'm inviting you to imagine this evening, and that my team will finish synthesizing and describing detail over the next 5 or 6 quarters, is not a fantasy. It is available, practical, and profitable now. At Rocky Mountain Institute, we know this because we're doing it. We do solutions, not problems. We do transformation, not incrementalism, and we're practitioners, not theorists. Now, quite often, politicians and the media administer to all of us a stupid energy policy multiple choice test, which, if it were clearly stated, would ask something like this: would you rather die of climate change or oil wars, or perhaps nuclear holocaust? Of course, a better answer, which we're seldom offered, is none of the above, and that's what we get when we use energy in a way that saves money, because then climate change, oil dependence, and nuclear proliferation all go away, not at a cost, but at a profit, because saving fuel costs less than buying fuel. Most of the negotiators at the Copenhagen Climate Summit somehow forgot that efficiency is cheaper than fuel, so they ended up discussing, not very fruitfully, cost, burden, and sacrifice. What does it cost to protect the climate? Who should pay, and is it worth it? They should have been talking about profits, jobs, and competitive advantage, and that would sweeten the politics so much that any remaining resistance to climate protection should melt faster than the glaciers. Now, a year ago, McKinsey and Company showed how to cut projected 2030 emissions of global greenhouse gases by 70%, very cheaply. In fact, the average cost ended up about $6 per ton of CO2, because the costlier stuff on the right, mainly on the supply side, got nearly paid for by the profitable energy efficiency on the left side. But I'm going to outline tonight how using newer technologies and integrative design can save even more energy and at negative cost. But do we have enough time? How fast must energy efficiency work? Well, if the energy used to make a unit of economic activity kept drifting down by just 1% a year, as it has historically, then carbon emissions would triple by 2100. Then we'd all be toast. Of course, we want to make toast, not be toast. So what if we could cut energy intensity not 1% but 2% a year? Well, that would stabilize carbon emissions. And if we could cut energy intensity 3 or 4% a year, that would reduce emissions enough to avoid triggering further climate chaos. But can we do that? Well, actually, yes. This country has routinely cut its energy intensity 2 to 4% every year for decades. And when we last paid attention, we cut oil intensity more than 5% a year for 8 years. China cut its energy intensity over 5% a year for a decade, actually for a quarter century. And after a few years lapse, they've nearly regained that pace now. Many big companies are making billions of dollars profit substituting efficiency for fuel, and the better ones are cutting their energy intensity, their energy per unit of production, by 6 to 16% a year. So why should 3 or 4% a year be so hard, especially since most of the growth is in places like China and India, where they're building the infrastructure the first time, and it's a lot easier to build it right than fix it later. And since everyone who does energy efficiency makes money at it, why should it be costly? Well, I want to tell you 2 main stories tonight about oil and about electricity, which is mainly a coal story. Oil and power plants each release over 2/5 of the fossil carbon going in the air. Let me start with the oil story. In 2004, my team published a detailed, transparent, Pentagon co-sponsored study mentioned a minute ago, winning the oil endgame. And it shows how to eliminate U.S. oil use by the 2040s, led by business for profit and facilitated by innovative public policy and by military leadership. We wrote it for business and military leaders. It's built around competitive strategy cases for cars, trucks, planes, military, and fuels. Now, the transition off oil could look like this. The use of oil in the solid red line and the imports of oil in the dashed red line are normally forecast to head toward the northeast corner forever. But we found that we could turn down along the green curves by redoubling the efficiency of using energy. We've already doubled it since '75, and we can double it again at an average cost of $12, year $2,000, for each barrel saved. And then we could go down more steeply along the blue curves by replacing the other half of the oil with a mixture of saved natural gas and advanced biofuels unrelated to the food system. That stuff has an average cost of $18 a barrel. So the average cost of getting off oil altogether is $15 a barrel. That's about 5 times less than we're paying for it. And I'm assuming here that all of the external or hidden environmental, social, security, and so on costs of buying and using oil are zero, a conservatively low estimate. The costliest barrel that we would save or substitute, by the way, costs less than $26. Now, technologically, the nub of the problem is transportation, which uses about 70% of the oil. But it turns out we can triple the efficiency of cars, trucks, and planes with no compromise but better safety just by making them lightweight, more slippery and moving through the air along the road, and giving them advanced propulsion. This often improves performance too, as with this Opel diesel hybrid concept car that gets 150 miles an hour and 94 miles a gallon, although not at the same instant. Tripled efficiency cars can repay any extra cost in about a year. Tripled efficiency trucks in less than a year, maybe a half year. Tripled efficiency planes in a few years. Blended wing body shapes like this have now had over 80 scaled test flights from Boeing. And a tripled efficiency for these 3 kinds of vehicles turns out to be equivalent to buying fuel at about 25 to 55 cents a gallon. Now, these kinds of breakthrough vehicles can serve all purposes and tastes. For example, 10 years ago, my team and 2 European Tier 1 engineering firms designed this uncompromised, safe, high-performance, halved-weight, mid-size suburban assault vehicle. It uses about 3.6 times less fuel than its steel equivalent. It's actually 67 miles a gallon on gasoline, or 114 on hydrogen. The gasoline version would sell for $2,500 sticker price, more than the steel equivalent, but that's because it's a hybrid. Making it ultralight does not cost extra because the costlier carbon fiber it's made out of is paid for, as I'll show, by simpler automaking and a smaller propulsion system. Now, Toyota has shown a carbon fiber concept car that has the same interior size as a Prius, but half the fuel use and a third the weight. It's a plug-in hybrid with a battery bank recharged by a tiny half-liter engine tucked under the rear seat. RMI's 5th spin-off, Bright Automotive, is ready to mass-produce this aluminum van that is about 3 to 12 times more efficient than normal, but unlike other plug-in hybrids, it doesn't need any subsidy to make a strong business case to the fleet buyer because its lightweight and low drag eliminate most of its costly batteries. And we're very pleased to be partnering with Duke Energy on some of this venture. To understand how this magic efficiency works, you just need to think a minute about the physics of a car. Our whole society is fueled with primeval swamp goo and dinosaur poop. There must be some more modern way to do this, but what happens to that fuel energy once you put the gasoline in the tank? Well, it turns out each day your car is using 100 times its weight in ancient plants And 87% of that energy never gets to the wheels. It's lost in the engine, idling, driveline, accessories. And then of the remaining 13%, roughly half of that is lost heating the air that the car pushes aside or heating the tires and road. And only the last 6% of that fuel energy accelerates the car and then heats the brakes when you stop. However, only a 20th of the mass you're accelerating is you. 19/20 is the heavy steel car. So only a 20th of 6%, or 0.3% of the fuel energy actually moves the driver. This is not very gratifying after 120 odd years of devoted engineering effort. However, the good news is that at least 2/3 of the energy needed to move the car is caused by its weight. And better than that, every unit of energy saved at the wheels saves 7 additional units that you don't need to waste getting it to the wheels. So every unit of energy you save at the wheel saves a total of 8 units at the tank. Conventionally, we just think about making the engine more efficient. You know, that's where the losses mainly are, so that's what Detroit concentrates on. It's like somebody asked Willie Sutton, why do you rob banks? He says, because that's where the money is. But when you save 1 unit of energy in the engine, you only save 1 unit in the tank. You don't get that 8-to-1 leverage. You're always better off, therefore, making the car radically lighter first. And to understand why it's not more expensive, this is what the structure of that SUV looks like that you saw a minute ago. It has only 14 parts, each made with 1 low-pressure die set. Well, an SUV would normally have 10 or 20 times more parts, each with an average of 4 progressive steel stamping high-pressure die sets. So you just saved about 99% of the nearly $1 billion tooling cost. Each of these parts can be lifted with 1 hand and no hoist. The big part on the side I can briefly lift with 1 finger. And these parts then snap precisely together for bonding without needing the robotic body shop. And if you lay color in the mold, you get rid of the paint shop too. Those are the 2 hardest and the costliest parts of making the car. They just went away. And you end up with about 2/5 lower capital intensity, at least, than the leanest plant in the industry. Now, new technology developed by one of our spin-offs can make ultralight carbon fiber structures like this test piece, which you can tell is really strong and stiff, in less than a minute. And when you scale this to automotive cost and speed with aerospace performance, then you get an ultralight car with the ultralighting for free. By the way, this is also tougher than titanium. Tom Friedman has whacked this real hard with a sledgehammer and done it no damage at all. And this new manufacturing technology is equivalent to finding a Saudi Arabia by drilling at the Detroit Formation. Very prospective play, because that's how much oil we would save if we made all our American cars and light trucks out of this stuff, because then half the weight and half the fuel use go away. It gets safer because this absorbs 12 times as much crash energy per pound of steel, and the car costs the same to make. Well, at RMI, we accelerate such breakthroughs partly by fostering competition. For example, we open sourced the whole hypercar concept in '93, and that leveraged our roughly $3 million R&D investment into about $10 billion of industry commitments, because they were all worried their competitors would do it first. We've spun off a couple of car companies, and also we do what we call institutional acupuncture, which means you figure out where the business logic is congested and not flowing properly, and you stick little needles in it to get it flowing. This works really well. It's about as much fun as you can have with clothes on. And our partners in doing this range from Ford to Walmart, from Boeing to the Department of Defense. But to take the world beyond oil, we really need to transform 6 sectors: cars, trucks, planes, fuels, military, and finance. I think 3 or 4 of those, are maybe more, are already at or past their tipping point. So there's still a lot of hard work to do, but it's starting to get easier. And last year, mainstream analysts started to see peak oil on the demand side. In April, the Wall Street Journal reported that ExxonMobil now agreed with many government and private forecasters that U.S. gasoline use had peaked in 2007. It would never get that high again. In September, Cambridge Energy Research Associates, the leading strategic consultancy to the oil industry, said the industrialized countries' total oil use had peaked in early 2005, if we never get that high again. And in October, a conservative analysis by Deutsche Bank based on electrifying new cars found that world oil use will peak around 2016, and then by 2030 will fall to about 8% below today's level, or about 40% below the consensus forecast. And by the way, they were assuming Chinese electrification of new cars at 1/3 the level that China is actually targeting. So in short, oil is becoming uncompetitive even at low prices before it becomes unavailable even at high prices. Now, my second big story tonight is about saving electricity and then making it differently. And in round numbers, 70% of our electricity is used in buildings, 30% in industry. 2 decades ago, my team looked at 1,000 technologies or so, measured cost and performance data, and when we added them up, we found that about 3/4 of all the electricity then used could be saved if you retrofitted those technologies wherever they would fit and make sense and make money. And the average cost of that saving would be, in today's dollars, about 1 cent a kilowatt hour. That's cheaper than running a thermal power plant, even if building the plant and the grid cost nothing. Of course, now the potential savings are even bigger and cheaper because the technology has improved faster than we've used it. So the low-hanging fruit, it's fallen down off the tree. It's mushing up around our ankles. It's spilling in over the tops of our waders, and the innovation tree keeps dumping more fruit on our head. But there's an even more important innovation in efficiency you might not have heard about. It's not in any official report yet, but we've proven it quite thoroughly at RMI, and it's called integrative design. It turns diminishing returns into expanding returns to efficiency investment. That is, it can make very large energy savings cost less than small or no savings. For example, let's go to my house in Colorado. This is at 7,100 feet in the Rockies, where temperatures have gone as low as minus 47 F. Midwinter cloud can last 39 days, and you can get frost any day of the year. We've had frost on the 4th of July. But this house is fossil fuel free. It's a net energy exporter. It's about 99% passive solar heated, and it has no furnace or other conventional heating equipment. But when you come inside, here's this emerging tropical jungle where we just harvested the 29th banana crop, and we're ripening 3 more. When I last measured it in 1984, the house was saving about 99% of the usual space and water heating energy, 90% of the electricity, leaving just $5 a month worth for 4,000 square feet, and it was saving half the water, and all that came with a 10-month payback. But today's technologies, which we just retrofitted, are even better, and soon I'll have the measurements to tell you how much better. The key is integrative design that gives multiple benefits from single expenditures. For example, this arch up in the upper left has 12 different functions, but only 1 cost. Hardly any element of the building has fewer than 3 functions. But it doesn't have to look like this to work like this. It can look like whatever you want, and it can be in any climate. For example, in an ordinary-looking new tract house, we've eliminated space cooling with better comfort up to 115 F and with lower construction cost. Or in Bangkok, a friend of ours applying the same principles got rid of 90% of the air conditioning energy with better comfort and no extra construction cost. The same approach works for big buildings, both old and new. For example, the Empire State Building, we helped design a retrofit for that they're implementing now, and that's expected to save 38% of the energy with a 3-year payback, thanks to integrative design. The trick is they're setting up a improvised temporary window factory on a vacant floor, and it's going to remanufacture those 6,500 windows on site into super windows that are almost perfect in letting in light without heat. So when you combine that with better lights and lighting controls and office equipment, you cut the peak cooling load by 1/3. But that, in turn, means we don't need to replace and expand the old chillers. Instead, we can renovate them in place and reduce them, and that saves $17 million. that helps pay for everything else and yields the 3-year payback. If you similarly retrofit and optimize as a system a 20-year-old curtain wall office tower near Chicago, you end up saving about 3/4 of its energy with a payback of minus 5 months. That is slightly cheaper than the routine 20-year renovation that saves nothing. Why is this approach then not more widespread? Well, because in conventional practice, the more you save, the more it costs, diminishing returns. And in conventional thinking, you invest in efficiency only until its marginal cost exceeds its cumulative present valued saving. That's the cost effectiveness limit where most people stop. But we found that if you keep investing beyond this limit, for example, putting twice as much insulation as normal in my house, you get to a point where suddenly your marginal cost goes down because, for example, in my house, we no longer need the furnace, ducts, fans, pipes, pumps, wires, controls, fuel supply arrangements. So it was $1,100 cheaper up front to build it with no heating system. And this is what we call tunneling through the cost barrier, because you don't want to get there the long way around. You should just go straight for that result to get expanding returns to investment and efficiency. And of course, your lowest risk investment is the one you don't need to make. The same approach works great in industry too. For example, about 3/5 of the world's electricity runs motors, half of that runs fans and pumps. And we can save about half the motor energy with a 1-year payback by 35 improvements to the existing drive system, 28 of which are free byproducts of the first 7. But first, before we do that, we should stop wasting most of the energy used by the pumps, fans, and other motor-driven equipment. For example, pumps, the biggest use of motors, move liquid through pipes. But a Dutch colleague redesigned a typical industrial pumping loop to use at least 86% less pumping energy and cost less to build just by using fat, short, straight pipes instead of skinny, long, crooked pipes. This is not rocket science. This is good Victorian engineering rediscovered. And the Singaporean master engineer who taught us that, Lee Eng-lok, just did this installation. It's a 69% saving of the usual pumping energy at lower construction costs, partly because the pumps, motors, inverters, and electricals all get smaller and cheaper. Now, if you think about the 60% of electricity used for motors as part of a larger system, well, from the coal burned in the power plant to the end use, there are all these successive compounding losses. So only 1/10 of the energy in the coal comes out the pipe as flow. But now turn that around backwards, and those compounding losses become compounding savings. Every unit of flow or friction you save in the pipe saves 10 units of fuel cost, pollution, and global weirding at the power plant. And also, as you go back upstream, the components get smaller, simpler, cheaper. You save the most capital as well as the most energy. My team has found such snowballing energy savings from starting downstream in more than $30 billion worth of industrial redesigns in 29 diverse sectors. And they're quite interesting examples we don't have time to go into here, but for example, our latest chip fab design is expected to save 2/3 of the energy and half the capital cost. Our latest mine design will run on no fossil fuel and no grid electricity. It runs on gravity. Our latest data center design is saving 3/4 of the electricity and has 4 times the normal computing capacity. But instead of that factor 16 intensity reduction, had they followed all our recommendations, they would have expected an 80-fold reduction in electric intensity and saved about half the capital cost. By the way, none of this stuff would be possible if the plants had been optimally designed in the first place. And I'm getting tired of redesigning stuff that wasn't designed right. So we have a project called 10XE, Factor 10 Engineering, which aims to reform how engineering is both practiced and taught. So for example, people will not anymore put in the textbook that you should optimize the thickness of your insulation without counting the avoidable cost of the heating system, or you should optimize the diameter of the pipe without counting the avoidable cost of the pumping system, because that's the mistake the textbooks make now, and engineers all over the world do it that way. We need to do it better. Just so you won't think this is quite so peculiar, let me just take you to that data center and show a little more thoroughly how you get a 2 order of magnitude leverage in energy savings. It's a little like we saw in pumping. Let's start upstream and see what happens. You put 100 units of, say, coal in the power plant, 30 watts gets through the power plant and grid to the data center. Half of that is lost in the cooling and power supply equipment that are half the capital cost of the data center. Half of the electricity that then gets to your server doesn't even get to the chips. It's lost in inefficient power supplies and a whole bunch of fans that take heat that shouldn't be there off the motherboard into the room so we can do dumb things with it. And then then you get power to the chips. About 9% of the original fuel energy gets to the chips, but most of them are sitting there cycling away doing nothing useful because of severe underutilization of resources, all kinds of computing resources. So the servers are largely idle most of the time, and yet they still draw almost the same energy. So let's take that little stalk coming out the bottom, that's on the order of 1% what you started with, and let's magnify, because otherwise it'll get too small to see. The next problem is bloatware. You have lots of inefficient or zero-value applications typically running, and then you may even have inefficient business processes downstream of that. So very, very little customer value comes out the other end. But let's start downstream and work back upstream to get compounding savings. The first thing to do is have lean business processes and elegantly terse code, beautifully compiled so that every compute cycle is a needed and wanted one. Then we buy servers 4 times more efficient, which cost the same. You just have to shop for them. Then you don't need very much cooling and power supply for them, and there are much smarter ways to do that than the conventional ones, and you can even get rid of half the utility loss, making your power and heating and cooling on site in a fuel cell. You get the idea how these savings multiply to give you 2 order of magnitude savings. Again, it's not exotic, it's just rigorously applying established engineering principles from a whole system perspective. I promised to say a little bit about the revolution in how we make electricity. And this graph tells the story. This shows worldwide how much electricity has been or is projected by industry to be produced by what The Economist magazine calls micropower. The larger red part of it is co-generating electricity in factories and buildings along with useful heat, and that combination typically saves at least half of the fuel, carbon, and cost. The colored wedges underneath that are all of the renewable sources except big hydro. Together, these kinds of micropower are now producing about 16% of the world's electricity. Nuclear is about 12 or 13. And they're producing about 2/3 of the world's new electricity. They're producing half to, or a sixth to over half of all electricity in a dozen industrial countries. This is not one of them. In the US, we're down around 7% because we have special laws and habits favoring incumbents and big plants. But all the big thermal plants put together, whether they're using coal or gas or uranium for fuel, have been pushed into minority market share and shrinking because they have too high a cost and too high a financial risk to be very attractive to investors. In 2007, for example, the US or Spain or China each added more wind capacity than the world added nuclear capacity. In fact, the US added more wind power that year than we added coal power in the previous 5 years put together. And in 2008, for the first time in maybe a century, the world invested more in renewable than in fossil-fueled power plants. The story of what the market is actually buying is shown here. Again, these are worldwide data showing the amount of generating capacity added in each year. The blue line is wind, the green, we don't have the 2009 data yet, is photovoltaics. The red is nuclear, which lost capacity each of the last 2 years. And in fact, in 2008, the last full data we had, just the distributed renewables, not counting big hydro, got $100 billion of private capital investment and added 40 billion watts of supply. Nuclear got and added zero. In fact, if you correct for capacity factor, because a nuclear plant puts out something like 3 or 4 times as much electricity per kilowatt per year as the photovoltaics do, the photovoltaics are so far ahead and growing so fast, nuclear may never catch up in annual output additions. And this whole micropower revolution, largely led by China, has already happened. Sorry if you missed it, but it's not too late to get in on it. Now, there's a lot of discussion these days of the nuclear renaissance, so I went looking for it, and I think I found it. This graph shows in blue the number of reactors that are listed each year as under construction since 1950 by the International Atomic Energy Agency, and the red dots are the corresponding capacity. Now, the nuclear renaissance is this little uptick right at the end, which has taken the new construction to a quarter the peak rate achieved in '79. So there are now 56 units under construction, amounting to about 4 to 4.5% of the new generating capacity under construction in the world. But I looked more closely at the 56 units, and there's a curious pattern that emerged. 13 of those 56 have been listed as under construction for over 20 years. 24 of them have no official start date. Upwards of half of them are late. 41 of the 56 are in 4 countries, centrally planned and rather untransparent power systems. 3/4 of the new starts are actually in China. All 56 are centrally planned, either by government agencies drawing on the public purse or by equivalent arrangements, and none of them are competitive free market purchases as we normally construe them, where they really have to compete against or get compared with their alternatives. The challenge the industry faces is partly that big peak of construction in the 70s and 80s has a later echo of retirements after 40 or perhaps 60 years if all the licenses get extended. So we're facing that huge peak of retirements coming at us in the next couple of decades, and you could somewhat shift that to the right by further life extensions if justified by safety and economics, but clearly construction will be hard-pressed just to make up for the retirement of the existing fleet. So if we want to get off coal power, that's half our electricity, what do we do instead? Well, first of all, there are some replacements for coal power that are cheaper than just running the coal plants, even if they're free to build or all amortized. If we used electricity as efficiently nationwide as the average of the top 10 states 5 years ago, we'd save about 5/8 of the coal power. If we bought all the electricity efficiency that is cheaper than fueling a coal plant, we'd save at least all, maybe more, of the electricity we make with coal. Then there are some other substitutions that are cheaper than building and running a new coal plant. For example, building the wind power that's stuck in the interconnection queue waiting for a hookup would save over half the coal power. The National Renewable Energy Lab on 4 February released a new assessment of U.S. wind resources. If you count just available land after all the land use exclusions, yielding at least a 30% capacity factor at 80-meter hub height, you can replace all the coal power 19 times over with that. And then there's industrial cogeneration. That's good for about 40% replacement, plus more in buildings, we don't know how much, plus some other renewables, we don't know how much, but we do know that if, for example, we just ran our coal plants less and our largely idle combined cycle gas plants more, then at an extra cost of roughly a couple of cents a kilowatt hour, we could save over 1/3 of the coal power. And if we put photovoltaics on 3% of the structures, we'd save all the coal power on an annual basis. Now, that is currently more expensive than coal power, even in most places, new coal power. However, by the time you could build a coal plant starting now, it appears the photovoltaics will be cheaper. For example, if you start, say, in New Jersey, or in your climate for that matter, building a new coal plant, and right next to it you start building a photovoltaic plant of identical annual output, by the time the coal plant can be built, the solar plant will be producing slightly cheaper electricity, just riding down the historic cost curve, which it shows every sign of continuing for a long time. Also, it'll produce about 2.5 times as much peak output on hot afternoons. And to build that solar plant, you had to build solar manufacturing capacity that can now reproduce that plant every 20 months. So if you built the coal plant instead, you'd probably feel some regret. Well, if you add all this up, you can replace the coal power over 22 times over without counting the question marks. And one way of thinking of that is you only need to put in a 19th of the available windy land's wind power to do the job. But of course, we're really talking about a mix or a combined transformation of efficient use and diverse dispersed renewable supply. And when you put all that together, they really flip the whole electricity sector on its head. Traditionally, electric companies like Duke Energy have relied mainly on giant coal and nuclear plants that respectively, worldwide, are causing climate chaos and spreading nuclear bombs. And then you augment them with giant gas plants, and then you buy a little efficiency and renewables. But those utilities are traditionally rewarded for selling you more electricity. But now in some states, we're starting to change the rules so the utility gets rewarded for cutting your bills. That's much smarter. That aligns your and their incentive. And where that happens particularly, the market is shifting massively toward efficiency, renewables, combined heat and power, or cogen, and other ways to blend them all together reliably. Now, this different structure is a better buy, and typically these better buys that are winning in the marketplace save about 2 to 20 times more carbon per dollar and about 20 to 40 times more carbon per year than a nuclear plant. So the verdict of the marketplace is also the most effective climate solution. And if we acknowledge nuclear's market collapse and help developing countries harness more modern options to get reliable and affordable energy for their development, that can also smoke out proliferators of nuclear weapons and help to end energy poverty, thus making the world richer, fairer, cooler, and safer. I had a little paper in Foreign Policy magazine, 21 January, pointing out that what developing countries will call for at the Non-Proliferation Treaty Review Conference in May, namely help with affordable, reliable energy for development, is exactly the same thing that the same countries asked for in Copenhagen, namely help getting off fossil fuel, and it's the same help many of them want getting off oil in particular. So I think with one solution, you might call it sunbeams for peace, we could actually solve 3 big problems. Now, if you combine the electricity and oil revolutions plus similar opportunities with natural gas and directly used coal, then you have a really big story, reinventing fire. And at Rocky Mountain Institute, we are focused on driving this business-led transition from oil and coal to efficiency and renewables. Probably the shortest path is just to let all ways to save or produce energy compete fairly at honest prices, regardless of their type, technology, size, location, or ownership. I wonder who wouldn't be in favor of that? Well, why don't we find out just by taking economics seriously? What I've just summarized rests on some very detailed practical experience and empirical evidence. I think it reflects where the smarter energy companies are headed in their coevolution with civil society, with a few governments helping while most governments struggle to catch up and some governments stand in the way. There's still too much old thinking, and as the oilman Morris Strong said, not all the fossils are in the fuel. But if you think anything I've said here tonight sounds too good to be true, I just would invite you to remember Marshall McLuhan's remark. He said, "Only puny secrets need protection. Big discoveries are protected by public incredulity." Thank you very much.